start our discussion of the practice exam 2 for exam 2. Okay, one moment. Okay, perfect. Okay, so let's start looking at some questions. So this first question is for each molecule, or in this case for molecule A, draw the 2 chair conformations for molecule A. We draw the Newman projection for each chair conformation, citing along the C2, C3, and C5, C6 bonds. You've been given reference carbon numbers, and as such, you should be able to, in turn, infer the carbon numbers of the remaining carbons. Okay, so continuing on, let's analyze the stereochemistry here. So carbon 1 here, this methyl group is up. So as a result, on carbon 1, we would place this methyl group in the axial up position. Carbon 2 just has hydrogens. You do not have to fill in the hydrogens, but it's useful for visualizing 1,3 diaxial interactions. Carbon 3 has a tert-butyl group, which is pointing up, has a wedge, and as a result, we draw the tert-butyl group axial up. Carbon 6 has the chlorine, which has a dash, so the chlorine is pointing axial down. Any questions on how we converted this dash wedge notation into our desired first chair conformation for this cyclohexane ring?
No.
Okay, so after a ring flip, carbon 1 is brought down, carbon 4 is brought up, and carbon 1 ends up here. The label was purposefully omitted on this second structure because you could draw an alternative view, but I feel it's important to identify and make sure that you're mapping your carbons appropriately, which is why carbon 1 ends up here. So in this case, our methyl is still pointing up, except it's now in the equatorial position. The chlorine is still pointing down, except it's in the axial position. And the hydrogens are still just hydrogens. The tert-butyl group on carbon 4 is still pointing up, except this time it is in the equatorial position. So we've drawn out each of our chair conformations for the following molecule. Okay, any questions on how we got these 2 chair conformations?
How come the chlorine is axial and not equatorial in the first chair conformation?
Because the chlorine's pointing down, and as such, it must be in the axial position to be pointing down. Okay,
but couldn't you have equatorial down as well?
Not with this current view and with the current carbon labels. After a ring flip, the chlorine is equatorial down, but there's no way to reflect this exact relative stereochemistry. There's no way to reflect this exact relative stereochemistry in this case, while still having the chlorine in an equatorial position. That's why I fixed the carbon. Does that make sense?
Yeah, it does.
That's part of why I fixed the carbon numbers to minimize the potential spread in how students draw this first structure. Because there are other ways of drawing it, but not when I fix the carbon numbers as so. Perfect. Okay, so now we're asked to draw a Newman projection, citing along the C2, C3, and C5, C6 bonds.
There's a quick question regarding the reverse chair conformation.
Yes.
For the carbon number 2 on the reverse chair conformation, is yes. The hydrogen that's pointing downwards, is it supposed to be towards the other direction?
Oh, I always end up making that mistake. Yes, it should be like so. Yes.
Okay, just making sure.
Yep, there we go. Perfect. Okay, so now looking down the C2, C3, C5, C6 bond, in this case, we're going to be looking at it from the following perspective. So as we can see, carbon 3 is here, carbon 5 is here. And now from here, we can fill in our substituents. So in this case, on carbon 3, we have a tert-butyl group in the axial position, hydrogen's equatorial. Behind that, we have 2 hydrogens. From here now, we have a methyl group in the axial position and a hydrogen in the equatorial position. Okay, looking at carbon 6, we have a hydrogen in the equatorial, chlorine in the axial position, carbon 5 just has hydrogens. So we're able to convert this chair conformation into a Newman projection. We talked about this in the chapter 4 lecture. Does this make sense to everyone so far? Any questions on how we obtained this Newman projection? So after a ring flip, carbon 3 is still here from this view. We're viewing it down the carbon 2, carbon 3, and carbon 5, carbon 6 bonds. So at carbon 3, we still have our tert-butyl group, except this time it is in the equatorial position. Carbon 2 in the back still has the hydrogens. Carbon 1, we have the hydrogen in the axial position, the methyl group in the equatorial position. Okay. Carbon 6, we have the chlorine in an equatorial position, the hydrogen's axial. Carbon 5, we just have hydrogens. So we've effectively filled in our 2 chair conformations and the Newman projections for structure A. Does this make sense to everyone so far? Any questions so far?
No questions.
Okay. So now we're asked to apply the same method of analysis to structure B. So looking at structure B, we're going to repeat this process of analysis. So in this case, our methyl group has a dashed stereochemistry. So in turn, the methyl group will be pointing down. So it'll be equatorial pointing down. The tert-butyl group in this case has a dash notation, so it'll be pointing down. The tert-butyl group is on carbon 3, so it'll be equatorial pointing down. And again, let me just check. Yes, it should be pointing this way. Okay. Chlorine has a wedge, so it's pointing up out of the page. So in this case, the chlorine would be equatorial pointing up. Does it make sense how we converted this dash wedge notation into our desired chair conformation? Any questions on this? Okay, so after a ring flip, carbon 1 is brought down, carbon 4 is brought up. So in carbon 1, the methyl group is pointing down, except this time it's axial down. Carbon 2, we still have our hydrogens. Carbon 3, our tert-butyl group is still pointing down, so it's axial down. Carbon 6, our chlorine is still pointing up, except this time it's axial up. So again, we're going to look down and view this structure, looking down the carbon 3, carbon 2 bond and carbon 5, carbon 6 bond. It's also implied by how this Newman projection template is provided. So from here, we have carbon 3 and carbon 5. On carbon 3, we have a tert-butyl group in the equatorial position. We have our hydrogens. Our hydrogen on carbon 1 is axial. The methyl group is equatorial. Carbon 5, we just have hydrogens. Carbon 6, the chlorine is in the equatorial position. Does it make sense to everyone how we converted this chair conformation into a Newman projection view? Any questions on that?
Could you kind of reassure how these carbons are lined up? If we're looking down carbon 2 and 3, shouldn't carbon 2 be the front one on the Newman projection?
You could draw it that way, but in that case, the Newman projection would look something like this. If you look down carbon 2, if you look down this alternative view, your Newman projection drawing would look a little bit different. So carbon 2 and 6 would be in front. And so in turn, you'd have your hydrogens. Carbon 3 would be behind that. Carbon 1 would be in the front. So it looks a little weird when it's in the front. And then carbon 6 would be in front. So it'd look like so. It would look like this if you were to look down the alternative view.
Okay. Okay, it makes sense.
The reason why carbon 3 and 5 are in front is this first methylene group is drawn pointing down.
Yes, I see now.
Does that make sense?
Yes, it makes sense, yes.
Perfect. I specifically chose this view because it highlights something that's important for the later problem.
Okay.
Yeah. Did that answer your question?
Yes, it makes sense.
Perfect. So from here, we're going to still...
But looking at the hello?
Yes, I can hear you.
Can you hear me? Oh,
Yes, I
I'm
can.
sorry. I'm driving, so it's hard. I'm trying to do this at the same time, but I see the original and the one that you just drew again, or the other one. They look identical. How is it different?
Sorry, which two?
For the Newman projection, that is the view that you preferred, and then the Newman projection that the other student proposed. They look identical.
They are. They're the same structure. However, in this case, one is looking at it from the front side, looking down carbon 3 and 5. The other is looking at it from the back, looking down carbon 2 and 6. So it's two views of the same molecule. And that in turn changes what substituents are in front in our view and what substituents are in back in our view. The audio is cutting out. Oh, sorry. The audio is very inconsistent. May I recommend asking the question in the chat, or you can try re-asking your question verbally. I just couldn't catch the full question.
Go ahead and move on. I was in a bad spot. I'm getting home now, so I'll be in a better spot to ask questions, but keep moving on. It's nothing imperative.
Okay, no worries. Sorry about that. Okay, so we're now asked to look at the Newman projection for our second chair conformation. So again, we're going to be looking down carbon 3 and carbon 5. So looking at carbon 3, we have our tert-butyl group, and this time it's in the axial position. We have our hydrogens on carbon 2. Carbon 5, we still have hydrogens. Carbon 6, the chlorine is axial. Carbon 1, the methyl group is now axial. So with that, we are able to fill out each of our Newman projection views and for each of these 2 chair conformations. Does this make sense to everyone so far? Any questions so far? Okay, so now what we're asked to do is we're asked to calculate the energy associated with steric and torsional strain for each chair conformation for molecule A and B. So I'm just going to quickly fill in the 2 chair conformations for molecule A. And I'm going to draw out the hydrogens here just to be explicit. Oops, that should be a chlorine. So again, this is just a repetition of what we looked at earlier. We're just redrawing our 2 chair conformations. And now what we're going to do is we're going to look at the energy associated with the steric and torsional strain found in each of these conformations. Nope, that should be a hydrogen. Yeah. So we're redrawing our 2 chair conformations, and then we're looking at sources of steric and torsional strain. So then, looking at this first chair conformation, we see that we have a few sources of steric strain. So what 1,3 diaxial interactions do we have?
First on the reverse chair conformation, I think on carbon 6, there should be a.
Oh, yep, that should be a hydrogen. Yep, perfect. Okay, so now that we've transcribed our 2 chair conformations from the previous, that we previously generated, let's look at some sources of steric and torsional strain. So what interactions are we dealing with here?
1,3 diaxial.
Yep, so we have a 1,3 diaxial interaction between a tert-butyl and a hydrogen, which costs us about 11 kilojoules. We have a methyl hydrogen interaction, which should cost us, sorry, not a methyl hydrogen. Yeah, we do have a methyl hydrogen. And what's the value of this methyl hydrogen interaction?
It's about 3.8.
Yep. Okay, and then we have a methyl tert-butyl interaction, which should be a little greater than a tert-butyl hydrogen. And how much steric strain will that cost us about?
Like 12?
Way more than 12, that's for sure. It'll probably be on the order of like 16 to 20.
Oh, wow.
Yeah. Because a tert-butyl hydrogen is roughly 11. A methyl tert-butyl interaction is much more severe, so it has a greater steric penalty associated with it. What else do we have? What else do we have? What other diaxial interactions do we have?
Chlorine hydrogen.
Yep, chlorine hydrogen. So we have 2 of them. And what's the value of that?
I think it's about 1 if I recall.
Yep, 1 kilojoule times 2, which gives us 2 kilojoules total of steric strain. Any other interactions that we'd like to note? I don't see any. So in total, we have 27, 30, 32.8 kilojoules. So we have 32.8 kilojoules of steric strain in the following structure. Let's look at our second structure now. Do we have any 1,3 diaxial interactions in the second chair conformation? Do we have any 1,3 diaxial interactions in our second chair conformation? What do we think? Yes or no?
Is that one with the tert butyl and the hydrogen? Equatorial?
The tert butyl is equatorial, so it's not engaging in any 1,3 interactions. But I know what you're potentially getting at. So there are no 1,3 diaxial interactions, but there are some gauche interactions. There's one gauche interaction in particular, and it's between what two substituents?
The chlorine and the methyl.
Yeah.
Yep, exactly. So we have a chlorine methyl gauche interaction, which costs us, what's the value of that? Roughly.
It's probably about 3.8.
It's actually about 1 kilojoule. It's the same value as a chlorine hydrogen diaxial interaction. Remember that methyl substituent gauche interactions, that steric strain is about equal to the A value for your substituent.
Yeah.
Yeah, but if you put 3, that would be fine. It's a little on the high end though, since chlorine.
There's a question I was trying to make sense of. Was the tert butyl, equatorial tert butyl?
Yes.
With the hydrogen, the equatorial hydrogen that's across from it?
Yes. So generally you don't see gauche interactions with hydrogens.
No,
and just because it's, think of it like a baseline almost. You're going to have interactions with hydrogens throughout, but they're not differentiating between your two structures, and usually interactions with the hydrogens are pretty negligible in terms of energy.
Yes, I understand how it doesn't work with the gauche interactions, but I guess my question is for a diaxial interaction.
Yes. In which structure?
For the tert butyl and the hydrogen, the reverse chair?
Yes. So since the tert butyl group is equatorial,
yeah,
it cannot engage efficiently in diaxial interactions with the hydrogen atoms.
Okay, yeah, the name says it all. Okay.
And the way I would think about it is a 1,3 diaxial interaction is really best defined as a gauche methyl interaction. And if we compare, if we think about the dihedral angle that would be separating this tert butyl group and this adjacent hydrogen, this dihedral angle would be about 180 degrees.
Yeah.
And so our substituents would functionally be anti, and they wouldn't be able to, despite how bulky the tert butyl group is, engage in appreciable diaxial interactions.
Yes, it makes sense.
Does that answer your question?
Yes, it makes sense. I was confusing the diaxial. I was trying to relate it to equatorial, but it makes way more sense now. I noted the chlorine methyl gauche interaction, but I didn't see the other one. Yeah.
You can end up with some things occurring when you have really bulky substituents diequatorial, but that's a very niche case. You know, that only occurs if you have like 2 tert butyl groups right next to each other equatorial, and then it's not really a diaxial interaction that's causing the problem. It's that really massive gauche interaction that's the issue.
Yes.
Does that make sense?
Yes, it makes sense. Yes.
Perfect. Okay, let's look at structure B. Would anyone like to comment on this problem? Would anyone like to comment on the overarching gimmick behind this particular set of structures? These set of structures have a pretty interesting relationship. If you've read ahead into some of the future chapters, you may be able to describe these two structures using a certain term. What are these two structures? What's the relationship between structure A and B? Would anyone like to posit a guess here? Yes, they are in fact enantiomers of one another. And why am I asking that? What is the relevance of that to this problem? Would these structures then have pretty similar energies for each of the 2 chair conformations because they're enantiomers?
Yes, but shifting that tert butyl will change its interactions, wouldn't it?
It would, yes. But what we'll see is when we do the energy calculations for these two chair conformations, we notice that the energy for the highest and lowest energy chair conformation are identical between the two enantiomers. Because the enantiomers are just mirror images, they'd have the same types of interactions in one of their chair conformations. So it's sort of an embedded, you don't need to know that to solve the problem, but it's an embedded way to apply knowledge that can be used to vastly streamline this problem. So we're going to treat it as if we didn't know these were enantiomers and just do the calculations as normal. So I'm redrawing these two chair conformations. And I'm drawing the ring flipped form. So again, we've already drawn out these two chair conformations. We're just redrawing them for the purposes of analysis. We're just redrawing these chair conformations for the purpose of analysis. Okay, so looking at our first chair conformation, what interactions do we have? Do we have any diaxial interactions in this first chair conformation?
No.
No. So what interactions do we have? Instead of diaxial interactions, we have another brand of Gauss interaction, a Gauss interaction between what two substituents?
The chlorine and the metal.
Yep, exactly right. We have a Gauss chlorine methyl interaction. And what's the value of that interaction roughly?
It's about 1, isn't it? Yeah.
Yep, about 1 kilojoule. Okay, let's now look at this next structure. We have a ton of diaxial interactions at play. What diaxial interactions are we dealing with?
Well, as you noted, we have the chlorine and the 2 hydrogens.
Yep, so in terms of our 1,3 diaxial interactions, we have 2 chlorine hydrogen interactions. So that's 1 kilojoule times 2 kilojoules. What else?
Well, the metal and the 2 hydrogens.
Sure. So we have a methyl hydrogen interaction, 2 of them. So 2 of them?
Oh no, it's with the I'm sorry, the terbutyl and hydrogen.
Yep, so we have a terbutyl hydrogen, which is about 11 kilojoules, a methyl hydrogen, which is about 3.8 kilojoules, and
a methyl terbutyl or terbutyl.
Exactly right, which we estimated to be around 16 to 20. So in total, we have 32.8 kilojoules of steric strain. So then, are we able to identify our lowest energy conformation for structure A and B? Can we identify that based on these calculations?
They are the same in energy.
Yes, exactly right. So for structure B, the chair conformation on the left is the lowest energy conformation. For structure A, the chair conformation on the right is the lowest energy conformation. For structure A and B, if we compare the energies of the lowest energy conformation, the lowest energy conformation for both A and B are identical in energy, which makes sense because they're enantiomers. So just to show this, we're going to draw the lowest energy chair conformation for molecule A and for molecule B. You may have to redraw your chair conformation template or use or draw out the ring flipped form. So for conformation A, the lowest energy conformation in this case, we'd have to show the ring flipped form. And we'd have to put our methyl group equatorial. Our tert butyl group equatorial, and our chlorine equatorial. For structure B, it's a little bit easier. In this case, we have the methyl group equatorial, the tert butyl group equatorial, and the chlorine equatorial. You have to be really careful that you don't flip the stereochemistry. Notice for structure A, I had to draw the ring flipped form in order to preserve the listed dash wedge stereochemistry. Does that make sense to everyone?
Yes.
Perfect. And on the actual exam, you'll have both templates side by side. So which molecule, A or B, has the lowest energy chair conformation? Or is it a tie? What do we think?
They're equivalent.
They're equivalent. A and B have lowest energy chair conformations with identical energies. So we can solve this problem using solely the principles from chapters 3 and 4. Though if you know that they're enantiomers, that makes this last question easier to answer. Any questions on this comprehensive cyclic analysis example? Any questions on this example?
No question.
Okay, so let's look at this next problem. So we're asked to draw the structure of 3-methyl pentane. Pentane 5, 3-methyl. We put the methyl at the 3 position. Okay, and we're asked to draw Newman projections for each of the conformations of 3-methyl pentane, looking down the C3-C4 bond following IUPAC numbering. Okay, so we're looking down the C3-C4 bond.
Sorry to interrupt, but a quick question.
Yes, please go ahead.
In this case, it wouldn't matter from what direction we count the carbons, right? Since
It would. Oh, well, oh yeah, in this case, yes, the counting is degenerate in this case.
Okay.
But in all other cases, I included IUPAC numbering just to avoid ambiguity.
Yeah, okay.
Does that make sense?
Yes, it makes sense.
Perfect, perfect. Okay, so we draw out on carbon 3, we have this ethyl group, and we have a methyl group, and we have a hydrogen. On carbon 4, we have a methyl group and 2 hydrogens. Now, before I go any further, I'm going to do a commonplace definition just to make my plot of energy versus dihedral angle a little bit less difficult. I'm going to identify my 2 sterically largest substituents, and I'm going to place them and separate them with a 0-degree dihedral angle. So this will be my first structure for 0-degree dihedral angle. Okay. Let's look at the rest of this problem. I'm also asked to calculate the energy of each conformation and draw a graph of energy versus dihedral angle. Okay, I can do that. So while I'm drawing these conformations and rotating my substituents 60 degrees, I'm also going to calculate the energies. So for this 0-degree conformation, what sources of steric and torsional strain are we dealing with? So what sources? Gauge applies if there's a 60-degree dihedral angle. In this case, our substituents are eclipsed.
Oh.
And we're in the eclipse conformation. So we have some, rather than Gauge interactions, we have some eclipsing interactions. And what eclipsing interactions do we see?
Well, we see the ethyl and the methyl.
Yep. And what would the value of that be, roughly?
Ethyl, methyl, eclipsing. I don't know it off the top of my head. I don't have it.
So what would a methyl-methyl eclipsing interaction be?
8.
For methyl-methyl, a methyl-methyl eclipsing is roughly, so a methyl-methyl eclipsing is roughly 11. So then ethyl is a little bulkier, so I'd expect it to be around 12 to 13 kilojoules. Because the A value for an ethyl group is 4, a methyl group is 3.8.
That was the question I was going to have. I was looking for A values today on the Canvas shells,
Mhm.
and I was looking through the note sets. Do you know what chapter or where I can find that? Because I couldn't find the A
It's in the
value.
chapter 3 and chapter 4 notes.
I looked in chapter 3 and 4. Okay, I'll have to look again.
If otherwise, they also have for ethyl, if we look at like an ethyl hydrogen interaction, like an ethyl hydrogen interaction is around 7 kilojoules. And we know like an ethyl methyl gauche is around 4. So it's a little bulkier than a methyl group. Did that answer your question?
Yes.
Because the
Quick
ethyl group
question
is
for this.
4.0. Yes.
Quick
please go
question
ahead.
for this one. We're just gonna be estimating, right? Like since we know like what some
You should estimate all of them that weren't explicitly in the table in chapter 3. So for
Okay,
example, you should have like a hydrogen-hydrogen eclipsing interaction. You should know that one exactly. And
Of
what's the
course,
value
yeah.
of that?
4, I
Yes,
believe.
exactly.
Yeah.
Okay, what about this methyl hydrogen eclipsing?
So for that one, I believe either 8. Is that right, or
Yeah.
7?
I think it's 6.
Methyl hydrogen is 6.
Okay,
Yep.
perfect.
So
Sounds
now-
good. So just look at the tables, and then from there we can the ones that are not explicit, we can always estimate them, right?
Yes,
then-
but your
okay.
estimations should be within 20 to 30%. And you
Okay.
can use A values. So like if you put 13, that's fine. 12 is 13. 10,
Oh.
that's not reasonable because it's below the lower bound for a methyl-methyl.
Of course, yeah. Okay,
Does that make sense?
That makes sense. All right, thank you.
Perfect. Okay, so now what we're going to do is we're going to rotate our back substituents 60 degrees, and we're going to look at the 60-degree conformation with a 60-degree dihedral angle separating our bulkiest substituents. Okay, so looking at this now, what interactions do we have? I don't think we have any, we don't have any torsional interactions, but we do have some other interactions. What do we call these other interactions?
You said gauche because it's 60-degree dihedral, right?
Yep, so we have gauche interactions between multiple substituents. These are steric interactions by their very nature. So what interactions do we have?
We have a methyl-methyl.
Yep, and what's the value of that?
Is that 8?
A methyl-methyl gauche interaction is about 3.8.
Oh, I'm okay. I was going the eclipsing, so I need to remember gauche is lower.
Yeah, and methyl-methyl eclipsing is 11, just for reference.
11. These A values are going to be tricky on this exam for sure.
I mean, you don't need to have the A values exactly, but your estimation should be reasonable based on the steric bulk of each substituent. Does that make sense?
Yes.
Perfect. Okay, what other gauche interactions do we have?
So we have the ethyl methyl.
Yep, and
And
what
I
would the
think-
value of that be,
I would
roughly?
approximate the steric strain will be about 5 kilojoules, 4 to
Sure.
5 kilojoules.
Based on the A value, it'd be 4. 5 is not an unreasonable guess. Does that make sense?
Yes, yes.
Perfect. So in total, that gives us 7.8 kilojoules of steric and torsional strain. Just to differentiate it, torsional interactions occur when you have eclipsing substituents. Steric interactions occur primarily via Gauss interactions. Does that make sense?
Makes sense.
Perfect, perfect.
A quick question, Professor.
Yes, please go ahead.
Since wouldn't this is just curious. Is so wouldn't the what's it called? The etho
Yes.
doesn't interact with the hydrogen,
Um,
or
unless it's directly eclipsed,
Mhm.
you don't view that as a source of steric or torsional strain.
Okay. And for the one that has the branch, the three branches, like I forget the name of it.
Like isopropyl or tert-butyl. In either
Yeah.
cases, unless it's directly eclipsed to a hydrogen, interactions with hydrogen aren't typically accounted for, and they're pretty negligible in terms of energy if they're not fully eclipsed.
Okay, and only when a cyclo, only when it's a cyclo atom that is like
Yeah,
covering that.
so when you're looking at cyclic systems, like a 1,3
cyclic.
diaxial interaction, it's not
Uh-huh.
the hydrogen that's the issue. It's the fact that the axial hydrogen is attached to a carbon. So you can think of a diaxial interaction as almost like a Gauss methyl interaction. Just like
Okay.
what we saw here. Yeah. So it's
Okay.
not really like the hydrogen alone is the problem. It's the fact you have a hydrogen that is in close proximity to your methyl group, because if you look down the Newman projection, like, let me show you. So like here, for example, when you have a diaxial interaction, it's not necessarily like this chlorine and this hydrogen. It's an interaction between the chlorine. Let me find one that's easier to see. Let's see. Okay,
Sorry, I got
here we go.
a little late.
So look right here, please.
Mhm.
So if we just pretended this wasn't part of a ring and we just looked at what was going on between this tert-butyl group and this axial substituent, if we just looked at what was going on between the tert-butyl group and our axial substituent, if we think about the dihedral angle between these substituents, looking at this dihedral angle, it's 60 degrees, right?
That's correct.
This diaxial interaction is really just another form of Gauss interaction.
Oh, perfect. Okay, sounds
So
good.
it's so like this tert-butyl group doesn't care that this hydrogen is close by,
Mhm.
but it cares tremendously if this hydrogen is branching off of a carbon and it's brought in close proximity to the tert-butyl group.
Oh, okay, perfect. All right,
sense?
that clarifies it. Thank you.
Perfect. Yes, of course. Okay, so let's keep going with this process. As you notice, the problems are much more analysis heavy on this exam because that's what we did throughout each of these chapters. Okay, so we rotate another 60 degrees. And now we have our fully eclipsed. Well, this is a lower energy eclipsed conformation. So what sources of torsional strain do we have?
The methyl-methyl.
Yep. And what is a methyl-methyl eclipsing interaction? What's the energetic penalty?
3.8.
Eclipsing?
Ah. 7, 8.
It's roughly 11 kilojoules. A methyl hydrogen is closer to 6.
Oh, I keep mixing up the Gauss. Okay, I'm sorry.
No worries, no worries. What would this ethyl hydrogen eclipsing interaction be? Approximately.
About 12 to 13.
Ethyl hydrogen.
Yeah. About a
Between
Just
7.
Yeah, between 6 to 7. Yeah, it's about the same as a methyl group. Whenever you see an ethyl group, think of it functionally almost identical to a methyl group. It's a little bulkier, but the numbers are about the same. Does that make sense?
yes.
Perfect. Okay, and what about a hydrogen-hydrogen eclipsing interaction? What would that look like?
That's 4 kilojoules.
Yep, exactly. Perfect. So like these two you would need to have exactly. Like methyl hydrogen, you'd need to have exactly. Ethyl hydrogen, it's a range because there's a little bit of estimation involved. So in total, we have 1721 kilojoules of strain, which makes sense because this eclipsing interaction has lower energy interactions compared to the first 0 degree eclipsing structure or eclipsing conformation. So the numbers that we're estimating are consistent with the qualitative estimation of strain. Okay, let's continue rotating our back substituents. So from here, we have our first 3 substituents drawn as normal. And now we have the following arrangement for our back substituents. So what interactions do we have here, if any? "180 degrees separating our bulkiest substituents." This is known as an anti-conformation. But even in the anti-conformation, we still have some interactions.
Yeah.
What do we have?
We have that gouge.
Yep. We have a methyl
About
methyl
3.8.
gauche interaction. And what is the value of this interaction?
About 3.8 kilojoules.
Yep, 3.8 kilojoules of steric strain.
Yes.
Perfect. Almost done. 2 more conformations to go. Next, we rotate one more time. And I believe we're accessing a degenerate conformation. No, we aren't. We aren't. This is actually a unique conformation. 240 degrees. I may make this type of question 30 points on the exam because it is taking a while to complete. Okay, so we have our third conformation. It's an eclipsing conformation. And what interactions do we have in this eclipsed conformation? What interactions do we have?
We have
Methyl
2
hydrogen.
Sure. So we have a methyl hydrogen interaction. We have 2 of them. And what's the value of a methyl hydrogen eclipsing interaction?
6.
Yep, 6 kilojoules. What about an ethyl hydrogen?
About 7.
Yeah, 6 to 7. Okay, so in total, we have 12 kilojoules plus 6. We have 18 kilojoules of torsional strain. Okay, last conformation, we rotate one more time, 60 degrees. And now we have the following. When you're answering this problem, please make sure you keep your conformations organized, because otherwise it'll be very hard for me to understand what is being presented if it's not organized, just like I'm organizing it out here. Okay, so what interactions do we have in this last conformation? So this is a gauche conformation. And what interaction do we have?
So we have steric strain between the methyl and the ethyl.
Yep. And I
It's
appreciate that you recognize that it's a steric interaction. And how much strain is introduced from this methyl ethyl gauche interaction?
Is it about 4?
Yep, it's exactly 4 kilojoules. Perfect. So then, from this information, which of our conformations is the lowest energy conformation?
The last one.
The anti.
So what's greater?
No, the
3.8.
anti-conformation.
Yep, the anti-conformation is our lowest energy conformation. But it's very close. The last one has a slightly higher energy methyl-ethyl interaction, while methyl-methyl is lower in energy. But 300 is very close. So in practice, the equilibrium partitioning between these two conformations, it'll be like very close to a 50-50 of both. Did that answer that question in the chat? But in terms of absolute values, this anti-conformation is our lowest energy conformation. Does that make sense? What is the highest energy conformation? What dihedral angle corresponds to our highest energy conformation?
The eclipse 22, I can't see what angle we had it at. Oh, our 0 degree.
Yep,
Yeah.
the 0 degree. So let's circle that. And this would be our highest energy conformation that I'll put an H next to. Okay, perfect.
Or 360.
So now we're asked to draw a graph of energy versus dihedral angle. So let's see, we go all the way from 0 all the way up to 22. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Oh, I can make them spaced a little far apart, a little more far apart than that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Energy in kilojoules as a function of dihedral angle in degrees. Okay. Yeah, we'll just have 0 be at the 0 line, 60, 120, 180, 240, 300. And anything more than that would be redundant. Okay, what would the energy be for 0 degree dihedral angle?
That was 22 kilojoules.
Yep. So it'll be right here. What about 60 degrees?
7.8.
Okay, so we'll put it right here. Okay, what about 120?
21.
21, okay. What about 180?
For the anti was 3.8.
3.8. Okay. What about 240?
18.
Okay.
And 4 for the 300.
Okay. Perfect. So we have our complete graph of energy as a function of dihedral angle. Okay, now we're asked to draw the lowest energy conformation, which would be 180 degree dihedral angle. So we'll draw that here. And then for the highest energy conformation, it'll be the 0 degree dihedral angle. Perfect. So with that, we've completed and answered all parts of this problem. Any questions on this problem? So just like the example that we went over in class, a classic conformational analysis problem. Does that make sense to everyone?
Yes, it makes sense. I just need to study the values. I'll make some flashcards from the table and that should be good.
Perfect.
Is that something for IUP or the IPAC or whatever? Are we supposed to know those values for that exam as well? A values?
Yes. Yeah. Well, you'll need to know the qualitative values. the ones explicitly asked for in the table, you will have to know exactly.
For the
For the
For
ACS,
that.
yes, yes.
for the
In some
ACS.
cases, they provide some strain values, but for the very common ones, you will have to know them.
Would it be possible for like us to use us to know the ones that we need to know, but you provide the ones that aren't as common?
Well, what I would say is for the ones that aren't as common, the point is not for you to get a perfect match in the energies. The point is to apply this idea of qualitative estimation to provide a reasonable estimated value for the amount of strain. So the point is not necessarily recall this exact A value, but for this problem, it would be recognize that an ethyl has more steric bulk, and thus the ethyl-methyl interaction is higher in energy.
But we will have to have that A value memorized. The ones, there is quite a few that we do have to have memorized as a regular value. So I understand what you're saying, that we're supposed to then build upon the memorization and then say, okay, this one's much bulkier, so it's going to have a higher strain. I get that, but I feel like to match what we're going to be expected for the ACS seems like fair.
For the ACS, you're going to be expected to know all of these strain values.
I know, I understand that, but you had mentioned that we would know the strain values, but then they would give you some of the other values. Didn't you say that?
Sort of. So I can show you what a type of question would look like in an ACS style, looking at these next few examples. And this may help provide context to my explanation. May we discuss these next two so that way I can explain how it fits in?
Absolutely. I was
Yeah.
just trying to make sure that we're not doing things that are redundant or don't need to be done if it's not what's the standard. Do you know what I mean?
Sure. So let's take a look at this example, and you'll see what I'm talking about in terms of qualitative estimation. So a common question is you'll be given a structure and asked to draw the lowest and highest energy conformation for the following molecule. So we're given this structure and we're asked to, in turn, convert this dash wedge notation into a chair conformation. So looking at our chair conformation, so I'm just going to draw one of my chair conformations because I'm going to have to, by virtue of the fact there are only two possible chair conformations. One of them will be the highest, one of them will be the lowest energy. So in this case, the isopropyl is dashed. So then the isopropyl is going to be pointing down in the equatorial position. Where will this ethyl group be? Axial or equatorial? Where will the ethyl group be? If it's pointing up, where will the ethyl group be then?
Equatorial.
Yep, exactly. And for the alcohol, since it's pointing down, will it be axial or equatorial?
Actual down.
Can it be axial on this third carbon? If it's pointing down?
Equatorial.
Yep, it would be equatorial down.
There you go.
Yep, perfect. Okay, let's draw the ring flipped conformation. Let's draw the other chair conformation. Note on the actual exam, I'll put chair conformation. If someone did draw, if someone did draw a boat conformation or half chair conformation, I would give them credit for the way the question's worded, but we're talking, let's focus on the chair conformations for now. Okay, so after a ring flip, the isopropyl group now gets moved axial. The ethyl group now gets moved axial. And our alcohol ends up axial. So then, which of these two conformations is our lowest energy conformation?
The one on top?
Yep, exactly. It has minimized our diaxial interactions and it only has a single gauche interaction. The second conformation is our highest energy conformation. as it has a range of highly destabilizing diaxial interactions. Does this example make sense to everyone?
Yes.
Yes.
Perfect. So looking at this next problem, we're asked to draw the lowest and highest energy conformations for the following molecule looking down C2 and C3. And you're welcome to take a qualitative approach. You're not asked to recall any specific A value in this problem, but you are asked to apply qualitative methods, and you wouldn't need any tabulated values to determine which substituent has more steric bulk. So for example, if we look down C3, C4, I'm going to start just by drawing a basic outline of what's going on. We're going to start with just a rudimentary view where we have our ethyl group, we have our hydrogen, we have our methyl group, then we have a second ethyl group, our chlorine, and then our hydrogen. Okay, so now we have our rudimentary outline. For those who are curious, for this exam, you don't have to worry about the stereochemistry, but a small amount of extra credit would be awarded if you correctly draw out the Newman projection and accurately portray the stereochemistry involved. So now that we have our rudimentary Newman projection, if we're trying to think a little bit about the potential highest and lowest energy conformation, I'm going to look at my bulkiest substituents, right? This ethyl group is really bulky. So if possible, my highest energy conformation will have both of my ethyl groups fully eclipsed. Okay, so we can conclude qualitatively then that the conformation with both the ethyl groups fully eclipsed would be the highest energy conformation. By the same token, the lowest energy conformation would have our bulkiest substituents arranged in an anti-arrangement. So then, we'd place our substituents anti to one another. And in turn, we have drawn the lowest energy conformation. Does this example make sense?
Yes, that makes sense.
Yes.
Okay,
So let's entertain a possibility here. Let's entertain a possibility where we can have any stereochemistry at this center. Well, how would we analyze this problem then? If we're just asked to draw the lowest energy conformation of the lowest energy stereoisomer of this molecule. Well,
the two largest substituents at 180 degrees.
Yep. So if we're optimizing for the lowest energy, we'd place our bulkiest substituents 180 degrees apart. And just as a curiosity, if we had a choice between placing the hydrogen on the right, which is the actual structure, or the hydrogen on the left, which of these two structures, which of these two stereoisomers would be the lowest in energy?
The one on top.
So what's bulkier, hydrogen or chlorine?
Chlorine.
Right.
Yeah. So do we want chlorine engaging in Gaussian interactions with the ethyl and methyl?
No, we avoid a chlorine
No, we don't want.
interaction.
Yeah. So then would the structure on bottom then be higher or lower in energy?
Higher.
So we have an ethyl chlorine and a methyl chlorine Gauss interaction, right?
Mhm.
Is that worse or better than a chlorine ethyl interaction only?
Oh, I see. Yeah, it will be the one at the bottom. I
Yeah.
wasn't paying attention to the atom at the bottom. I wasn't.
So,
Yeah.
so if you were considering just any possible stereochemistry, this structure would be the lowest energy stereoisomer. And you could arrive to that conclusion without doing any calculation. You can just look and see, well, ethyl's bulky, ethyl's the bulkiest substituent, and we want to keep our chlorine away from everything else as much as possible.
That's correct.
Does that make sense?
Yeah, that makes sense. I wasn't paying attention to the atom at the bottom. That one.
Now, to apply this, if we're asked to draw the highest energy conformation in an absolute sense, would we want to have our methyl eclipsing with a hydrogen or chlorine? What is bulkier, a hydrogen or chlorine atom?
The chlorine.
Yeah, so the highest energy stereoisomer conformation would be the conformation that has the methyl and chlorine eclipsed. And we can figure that out without having any A value per se, but just because we know chlorine's bigger based on atomic radius and atomic size.
But that's good for these questions. But the 30-point question that depends on the A values, which 30 points is quite a substantial amount on this exam. That was what I was referring to.
Do you actually need any? The only unique value is the ethyl methyl interaction. And in that case, even if your value drifts by 1 to 2 kilojoules, you'd still be able to arrive at the qualitatively correct solution. That
And there's no problem. I can definitely memorize them. I'm just looking at this going, what is that the most priority for my time? Like, I guess I was just trying to wanted to pick your brain on this ACS exam. And I understand the qualitative and the quantitative.
What I'm saying is you don't necessarily have to know exactly that this ethyl group has a value of 4.0. You can estimate based on the relative steric bulk. That's why when
okay, so then if I chose that this was not, the lowest energy was not at 180 and I chose it at 300, would that be correct?
It would be qualitatively incorrect, because if we look at these interactions, ethyl is bulkier than methyl, right? And as a result, this ethyl-methyl interaction is higher in energy than a methyl-methyl.
Right, but so that's 3.8 and that's 4. So I would have to know the A values to get this answer correct.
Even if we covered up these A values and we were just looking at this without doing any calculations, wouldn't we agree that the ethyl group is bulkier and would have more steric strain associated with it than a methyl group?
By 0.2 kilojoules.
Just for getting the 0.2, without looking at the A value, just qualitatively for a moment, if we get out our model kit and we put an ethyl and a methyl group side by side. So we have our ethyl and a methyl group side by side. Would we not agree, just looking at the size of these substituents, that the ethyl group takes up more space and has more steric bulk?
Absolutely. I think I hear exactly everything you're saying, and I'm not going to waste the class time anymore. I want to complete with the exam, but I don't think you hear what I'm saying, because I would have to use A values to get this question correct, and then to also show the logic and where I get that, because I couldn't just say this is lowest and I could tell you qualitatively, because I can't do that on the exam for this question. That's all I'm saying. So I get what you're saying. I will follow along and I will memorize. No big deal. Keep going.
So looking at the next question. So in this case, we're able to draw out the highest energy and lowest energy conformation through qualitative comparison of the bulk of our chlorine, ethyl, and methyl groups. We concluded the ethyl groups have the greatest amount of steric bulk, and as such, if we place these ethyl groups eclipsing, we'd have the highest energy conformation. Does this example make sense? Any
Yes.
questions? Perfect. Okay, let's now do some naming problems. So in this case, we're asked to name the following compounds. You can do a lot of practice with this using ChemDraw. So first, we have to identify the longest chain that has the most branching. So the longest chain is a 6-carbon chain. We have two methods that we can count down the chain. We can either count using the method in black or red. And from here, which of these counting methods give us the lowest locant number for each of our substituents in counting order? Which counting method is preferred? So
The one
side
on
by
black?
side. Yep, exactly, because 2 is less than 5. So at our 2 position, what group do we have? Well, we have a methyl group. At position 3, what group do we have?
Ethyl?
Yep. And at position 4, what group do we have?
Methyl?
Yep. Okay, so what is first alphabetically?
E?
Yep, so ethyl is first alphabetically. We have 2 methyl groups, so what prefix do we use?
Dimethyl?
Yep. Okay, and it's a 6-carbon chain, so what do we call that? Six carbons. It's not cyclic, but removing the cyclo prefix, what do we call 6 carbons?
To be honest, I need to go back and review those terms.
So the 6th carbon is the hex prefix, so this would be hexane.
Hexane, there you go.
Yeah, and when it's cyclic, it would be cyclohexane. And I think that's what you were getting at earlier.
Yes.
Does this make sense?
Yes.
Perfect, perfect. Okay, let's look at this next example. And why is there stereochemistry here? Did we learn about a method to name disubstituted cyclic systems? Did we learn of a method to name these types of compounds using cis-trans nomenclature? Do we have a method to identify the relationship between these substituents? Is that a cis or trans relationship? And I'm going to draw something out to help you see it. So do we have a cis or trans relationship between substituents? This methyl group is up. This isobutyl group is pointing down. What do we call it when our 2 substituents are on opposite faces of the ring? What do we call that? From chapter 4, remember we discussed cis and trans isomers of cyclohexane, cyclopropane, and other cyclic systems. What do we call it when our substituents are on opposite faces of the ring? In this case, this would be the trans stereoisomer. So this would be trans. Okay, now let's name the rest of this compound. So we have 1, 2, 3. So we have a choice between placing our methyl group and our isobutyl group first. So what's first alphabetically? Isobutyl or methyl? Iso is one of the few prefixes that is actually counted. So what's first alphabetically? Isobutyl or methyl? I is first compared to M. So isobutyl will be first alphabetically. So then, if we have a tie in numbering, which substituent would get our lowest locant number? The methyl group or the isobutyl group?
ISO.
Yes, the isobutyl. So this would be trans 1 isobutyl. Then what's the locant number for the methyl?
3.
Yep. So it'd be 1 isobutyl, 3 methyl cyclohexane.
Can you go over the trans and what is the other one that you were saying?
Yes, cis and trans. So
Cis.
trans occurs when they're on the opposite face.
Opposite face.
So for example, in this case, our methyl is up, our isobutyl is down. Cis occurs when they're on the same face. An example of this would be if the methyl group and isobutyl group were both pointing up.
Oh, I see. Okay.
Does that make sense?
Perfect. Yeah.
And you can see that in the chair conformation by virtue of the fact that when you draw out the chair conformation, both of your groups will be pointing up.
Okay. Sounds
Does
good.
that make sense?
That does make sense. Okay. Trans.
Perfect. As a general rule, if you assign the substituents as pointing up or down, if they're both up or they're both down, it's cis. If they're different, they're trans. And this only applies when you have two substituents, because we haven't learned about the more complex methods of stereochemical labeling quite yet. Does that make sense?
Yeah, just two substituents, trans and cis. All right,
Yep.
perfect.
Perfect. And I believe that's on page 30 of the chapter 4 notes. There's an example with the cyclopropane early on, and then with cyclohexane towards the end.
Okay, perfect. That's something I need to review, just names.
Perfect. Okay, so now we're asked to draw a structure for the following name. So you asked about the cis stereochemistry, and I have an example that accommodates it. So let's break this name apart. So the substituents are in the front, the main chain is in the back. So cyclobutane, what is cyclobutane? How many carbons? Bute corresponds to how many carbons?
Four.
Yep. Cyclo, cyclic. Okay, we have a methyl at the 1 position. Okay. Oh, this name is messed up. It should be 1-butyl 4-methyl following numbering. So we have our butyl at the 1 position. We have a methyl at the 4 position. And because they're cis, should I draw the stereochemistry where they're both? How should I draw the stereochemistry? If I pick the methyl to have a wedge, how should I draw my butyl group? Should I draw it with a dash or a wedge?
A wedge, too.
Yeah, exactly. So we have 1-butyl 4-methyl cyclobutane. Does this example of translating a name into a structure make sense?
Yeah, a quick question, Professor. Why 4 rather than 2? Because I can see that you can go to the
yeah, that would be better actually. 1-butyl 2-methyl counting this way. Yeah.
Oh, okay, perfect.
That would be the full correct name following IUPAC.
Okay, perfect.
Yep, perfect. I think I was starting with a cyclopentane example and I changed the main chain without changing the numbering. But yeah,
okay.
you're correct. It should be 1, 2.
Okay, sounds good. So I can, perfect.
Okay, now we're dealing with some acid-base questions. We're asked to draw the products of each acid-base reaction, enter the pKa value for each reactant and product, and indicate whether the reactants or products will be favored at equilibrium. Okay, so we have a ketone. What is the pKa of a ketone alpha position? Approximately, give or take. It's about 20 to 22. I'd say 22 to differentiate it from the aldehydes. We have ethoxide. Ethoxide is going to react and pull off a proton. We're going to in turn generate a ketone enolate and ethanol. And what is the pKa of ethanol, roughly? What is the pKa of a primary alcohol? Give or take. Approximately, what's the approximate pKa of ethanol? It's about 17. So then, looking at our difference in pKa, 22 minus 17 is positive 5. The difference in pKa between our reactant acid and our product acid is greater than 0. So this reaction is reactant favored. Generally, the equilibrium favors the production of the weaker acid, as we discussed all the way back in chapter 2. Does this example make sense to everyone? Any questions on this example?
Can you go over it? Because this type of problems, I have a hard time trying to understand them.
So
Especially
looking at our pKa values, the ketone has a pKa of 22, the alcohol has a pKa of 17. So we can conclude the alcohol is more acidic since it has a lower pKa.
Oh, can we just look at the number? Because I see that you did the calculations. Can we just the number? Just looking at the numbers, right? 17 is yeah. All right.
So looking at the difference in pKa, you don't even have to calculate this. If you just have the pKa values, the equilibrium will generally favor production of the weaker acid. So what's the weaker acid? Which has the larger pKa? Is it on the left or the right?
Well, the left.
Yep, the weaker acid with the larger pKa is on the left. So the equilibrium will favor the left, which is our reactants. Does that make sense?
Yeah, and now when you're doing that, when you pull up the proton, like you always pull up from the end of the drying molecule, or how do you know?
You're generally going to pull off the most acidic proton. For the ketone, it's on the alpha position. For the alcohol, it would be the one attached to the oxygen.
It's life.
Does that make sense?
Yeah. Yeah. For this one, I do see it. But sometimes, like when there's other molecules, a little more complicated. I'm not sure how to distinguish where to draw the proton.
And that's based on the proton pKa's.
Oh, okay.
So the reason why we don't go after like this hydrogen is because this hydrogen has a pKa of like 42. So it's
which hydrogen?
The reason why we don't go after this one that I've drawn right here is because this hydrogen has a pKa of around 42. So you're never really going to pull off this hydrogen under the conditions because it's much less acidic than the hydrogen attached to the alcohol.
Okay, sounds good.
Does that make sense?
That makes sense.
So you can use pKa values to rationalize and identify the most acidic proton. And we actually did a few examples like that in the chapter 2 notes as well.
Perfect. So something else to review.
Yes.
All right.
Okay, so let's look at this next reaction. So I'm going to draw out this tert-butyllithium in the ion form. Sometimes organometallic compounds are drawn with a bond to lithium, but it's this tert-butyllithium really looks like this. It's the following anion. So first we have acetylene. What is the pK of this acetylene derivative? What is this pK of this alkyne proton? What do we think? What is the pK of an alkyne proton, roughly? It's about 25. So after an acid-base reaction where we pull off our proton, that in turn gives us the acetylide anion, and that gives us the following hydrocarbon. What is the pKa of a generic hydrocarbon about? What is the pKa of this proton? Roughly. Approximately. Order of magnitude, value. This would have a pKa of anywhere between 46 to 50. So then, looking at this acid-base reaction, considering that acid-base reactions favor production of the weaker acid, the equilibrium favors the weaker acid, is this equilibrium reactant or product favored?
Product.
Exactly. Now, if you didn't know the pKa values, then you can use a more qualitative argument. You're going from an sp3ch to an you're going from an spCH to an sp3ch, and we know qualitatively which of these protons is more acidic, the one attached to an sp carbon or an sp3 carbon.
SP.
Exactly. So even if you didn't know the exact pKa values, you can still complete the majority of the problem.
Oh, perfect. That's nice. That's good to know.
Yeah,
I like that. I like that better. I can see that better. All right.
perfect. So
Oh, and another question. What happened to the lithium? Like, did they just it goes away or?
the lithium ends up paired with the other anion at the end. I just didn't draw it for clarity.
Uh-huh.
It's
Oh, okay, but
mostly just floating around in solution.
oh, they just flow around. Okay.
Yeah,
sounds
it's just
good.
a countercation.
Oh, okay. Sounds good.
Mhm. Okay, now we're doing some simple selection of the most acidic molecule. So for each pair, we're asked to circle the most acidic. So what do we think? The one on the left or right? Ethanol or chloroethanol? What's more acidic?
The one on the right.
Yes, and what's the main effect?
I was just gonna basically gonna derive well to what you said. This one it will be in and it's next.
So you can't quite use a hybridization argument here,
Yeah.
but what is that chlorine doing? Does that chlorine exert an effect?
Oh yeah, it's pulling it's pulling the it's more basically electronegative, right? It's
Yes.
pulling more.
Yes, and it exerts an inductive withdrawing effect.
There
And
you go.
inductive effects increase the acidity of adjacent protons and stabilize basic anions. And because this chlorine is present in the structure on the right, by inductive effects, this alcohol proton becomes more acidic.
Perfect. All right.
Does that make sense?
That makes sense. Yeah.
Okay. What about this pair? We have a thiol as part of thiophenol and cyclohexane thiol. Which of these two compounds would be more acidic?
Would it be the one on the left?
Yes, and would you be able to provide a reason why?
The electrons are more localized.
Are more what?
Localized. They're like on the
Localized?
what? Like you cannot delocalize that. Like, oh, you can delocalize like.
Yeah, exactly.
There you go.
can stabilize the anion via resonance. And
There you
because
go.
the anion stabilized via resonance, the proton's more acidic. Exactly.
go.
Does that make sense?
Yep.
Yep. Perfect. Okay, what about these two? You have a tertiary and a secondary alcohol. What's more acidic? It's a minor effect until it's no longer a minor effect. It's these subtle things that can have dramatic impacts in the selectivity of reactions. Which one's more acidic? Substitution effects. We know substitution impacts the ability of solvent to coordinate. More substituted alcohols and more substituted anions are less able to interact with solvent and are less stabilized by the solvent. Based on that argument, would a tertiary or a secondary alcohol be more acidic? The secondary alcohol would be more acidic because when you generate the anion from the secondary alcohol, you're able to better coordinate it with solvent. There is less steric bulk interfering with ion dipole and hydrogen bonding interactions with the solvent. This leads to a pKa value difference of about 1 pKa unit, which seems subtle, but that's a 10 times difference in relative acidity and a 10 times difference in relative concentration of the conjugate base and the acid. Okay, now I'm asking you to circle the most basic molecular ion. So we have an sp versus an sp3 ion. What is more basic? Remembering that basicity, strong acids produce weak conjugate bases. So with that logic, which of these molecules, the sp or ions, in this case, the sp ion versus the sp3 ion, which of these ions would be most basic? Thinking back to the example that we, oh, sorry, this should be sp. This should be sp2.
Yeah.
So which
That
of
one
the-
right there.
The
sp2?
sp2?
Mhm.
So if we think about anion stability and we think about orbital energy,
Mhm.
we know that an sp3 orbital is the highest, followed by the sp2 and sp. So then this sp2 anion, would it be more or less stable than the sp3? Would it be more or less stable?
It will be can you rephrase that? Right?
So orbital energy, we know sp3 orbitals are the highest in energy, followed by sp2 and sp. Since the sp2 orbital is lower in energy, would this anion be more or less stable?
It will be less stable.
If it's lower in energy, if this orbital is lower in energy and we're holding this anion in an sp2 orbital, would this anion in turn be lower or higher in energy? It would be lower because the orbital is lower in energy, right?
Yeah.
And when we think about basicity, things are more basic when the anion is less stable. So because the sp2 anion is more stable, is it going to be more or less basic as a result?
More basic, right?
So since it's more stable, it'll be less basic. By the same argument, this sp3 anion is less stable. And in turn, because this anion is less stable, will it be more or less basic?
I'm not really understanding.
So the less stable your anion is, the more basic it is.
The less stable it is.
Yes, the more basic.
And you said that sp3 is the more stable, right?
sp3, looking at orbital energies, it's higher in energy, so it's less stable. So because the sp3 anion's less stable, is it going to be
Perfect. So sp3 is the less stable and sp is the more stable. So
Yes.
basically it will be more it will be more acidic, right? Or is the opposite? It will,
Yeah, so yes, so the sp2 hydrogen, this hydrogen, yes, is more acidic. But this anion, because it's more stable, the anion is less basic. Does that make sense?
yeah, okay, I see it.
And because the sp3 anion is less stable, in turn, this anion is more or less basic.
Oh, it's more basic, right?
Yes, exactly, exactly.
Yeah.
Does that line of argument make sense?
Yeah, so can we draw it will help if we draw the other one right first and then
Yes. So you can also tackle this problem by looking at the acids, and you know that an sp3 CH bond is less acidic. So in turn, this anion would be more basic.
oh, okay, perfect. All
Does
right.
that make sense?
That makes sense.
Perfect. So by the same token, if we compare this amide anion versus this phosphide anion, which of these anions is more stable? Which of these anions is more stable? Considering atom effects here. This is a classic example of atom effects. Considering atom effects, which of these anions is more stable? The anion on nitrogen or phosphorus? What do we think? We know anions are more stable on larger, more electronegative atoms, with atomic size having a greater impact on anion stability. So with that in mind, which of these anions would be more stable? The anion on nitrogen or phosphorus?
Nitrogen,
Which atom is larger, nitrogen or phosphorus?
phosphorus, but
Yep.
electronegativity goes from the bottom of the
Yes, yes. And as we mentioned, atom size has a greater impact than electronegativity. So then, which of these anions would be more stable?
the one right, phosphorus. Okay.
So then, which of these, remembering that more stable means less basic. This anion is more stable on phosphorus. So then, which of these two anions is most basic?
Phosphorus, right? Because it's more.
More stable means less basic. So then, because this anion is stable, it doesn't want to react as readily.
Mhm.
So because this nitrogen anion is less stable, which of these anions would be more basic then?
Why is it so complicated? Nitrogen?
Yes, exactly. The less stable anion is always going to be more basic. So this nitrogen anion, this amide anion, would be more basic. You can also make this argument by comparing your two parent acids. And you know that this amine has a pK of around 35. This phosphide has a pK of around 25 to 30. So in comparison, because the phosphorus parent acid is more acidic, this conjugate base would be less basic. So there are two routes to reaching the same conclusion. Does that make sense? And we did a few
Yes.
examples of this in the chapter 2 notes.
Yeah, I'm writing it down right now because I struggle with this one.
Perfect. And I can actually show you where that is in the chapter 2 notes, just to provide clarity. Allow me one moment to find it. I think we also did examples of this as well in the homework, but here's the section on ranking effects on acidity. Did that answer your question?
It did, thank you.
Perfect.
I just took a
Perfect.
photo of that.
So we finished discussing the exam. So what we'll do is we'll archive the